Welcome to the African Plants Georeferencing Train the Trainers workshop. This is Q&A session 3, and we're going to deal in particular with the concepts and protocols and processes that we have seen during module 5, which was integration of all the knowledge needed for georeferencing. So to start, I'm going to ask you to go to the Menti page that we have used before. Use this code on the screen. We will paste it on the chat as well. You can also access it through the QR code. And I'm going to move to that, to the Menti and present. Okay. So our first question today is, which are the necessary attributes in a georeference? That is, when we provide a georeference, which are the things that we need to report? You will see that to answer this question, you can grade it from absolutely indispensable to from not indispensable to indispensable, and you have grades in the middle if you consider that is needed but not indispensable for each of these attributes here, which are georeference protocol, georeference sources, latitude and longitude, geodetic datum, uncertainty georeferenced by, locality description, and georeference remarks. And so we will give you a moment to complete this. Do you have an answer? Here, what you're seeing on the screen is the 5 represents indispensable, and the closer to the center represents less needed, not utterly necessary. And the values we're seeing is the average of all the responses that we're having. Okay, I'll just wait a moment more because I know there are more people in the room. John, do you know of anyone who's having connection issues coming and going? Okay. No, just to know if we're expecting more answers or no.
Yes, 4 more answers.
Okay. So we'll give it a moment more. It's very interesting what we're seeing on the screen, really. And I'm thinking that maybe I should have clarified at the beginning that this is for a location that can be georeferenced. For those difficult localities that cannot be georeferenced, that's a different story. Maybe I should have clarified that at the beginning. Okay, we have 11 responses. And more people coming in. Okay. All right, I think I'll start looking at these results now. So, assuming that we have location that we can actually georeference, is not one of those cases where we cannot find the place or where it has inconsistencies and those kind of things. Assuming that we can georeference, there should be 3 elements, at least 3 elements, that we need for a georeference. If we're performing a georeference, our result will have, at a minimum, latitude and longitude, geodetic datum, and an associated uncertainty. So this means that this should all be up here, the dots, meaning they are absolutely necessary. Otherwise, we don't have a georeference. The others we're going to discuss a little bit in a slide that I'm going to show in a moment. But this one here, to me, is super important that you all understand. If we don't have coordinates, we don't have a georeference. For locations that can be georeferenced. If we don't have the geodetic datum, the coordinates mean nothing, basically. And if we don't have an uncertainty, we don't have a georeference because we're providing coordinates, but we have no error associated. And so these 3 elements are the elements that make up a minimum georeference. Anytime that we want to provide a georeference, these 3 elements have to be there. This under the point radius method. If we are using other methods, we may have different parameters that we need to inform. Now let me go back to the presentation here. And so we have here listed on the screen all the things that we had on the Menti, except also we included here georeference date that didn't fit in the exercise before. But we have them all here: latitude and longitude, datum, uncertainty, georeference protocol, georeference sources, georeference date, who georeferenced, the remarks, and the locality description. As I was saying, these three elements, coordinates, datum, and uncertainty, is the minimum that we have to provide to have a georeference. So a minimum georeference will have these three elements if we're working with the point radius method. Of the other elements on the screen, if we want to provide a good georeference, we should also provide the protocol, the sources including the dates of those sources, the georeference date, and who did that georeference, who made the calculations. So this is the minimum. If we want to be better, if we want to follow best practices, we should also report these other things. About georeference remarks and locality description. Well, georeference remarks we may not have. Sometimes georeferences are pretty easy, and so we don't have any comment to make. And so remarks may be needed or may not be needed. It depends on the particular case. So these are extra information. This is extra information that we have to report if it's needed. And then the locality description, we will only have it if it is available. For example, if we have a location that has a description that only has coordinates and we don't have a locality description associated, we don't have to make one up. So if it's not there, it's not there. Now, if it is there, it is best practice to keep it. Of course, we always have to keep the original information. But this locality description does not make up a georeference. It's very useful. It is very important. It is very important that we learn how to provide a good locality description. But for the georeference, these are the elements that are needed. You have to keep this in mind and have it very clear. So if anyone has any questions about this, please ask them, open your microphones or use the chat. Is this clear?
Yes, of course.
Thanks, Pascal. For the rest, is it clear? You can say okay or put thumbs up. Or...
Yes, it's clear.
Okay, thank you. Some yes on the chat also.
A bit, it's not clear for me on georeference protocol. Can you please give me some other hints for that, please?
Yes, for the georeference protocol, we would report which is the method that we're using. And so in this case, for the protocol, if we're using the point radius method, we would cite the protocol that is in the georeferencing quick reference guide. That is our protocol. Is a document or a set of rules, something that can be referred to, can be a citation, a paper citation, that describes which protocol we are following for doing the georeference. And so, for example, I'm going to go out of this, sorry. I'm going to go to the GeoPic. For example, here, when GeoPic provides the protocol, you see that it cites directly the Georeference Quick Reference Guide, because that Georeference Quick Reference Guide is giving you the steps that you're following to perform the georeference. If you're using some other protocol, you will have some other citation here, some other reference that what it's doing is tell other people which were the steps that were followed, basically. John, do you want to add something? Go ahead.
Yeah, do you have your georeferencing calculator open? Because there's a choice in a drop-down box there too.
Yes, I have the calculator open here. And so in here, when we calculate, we can have, well, here are two quick reference guides. One is the older guide, and this is the new one. And so if you were using the older one in which some of the steps were different, you would have to cite this one. If you're using the new one, you should cite that other one. If you were using some other protocol, you should give the citation or the reference of that protocol that you were using. In this course, we're using this one, the Georeferencing Quick Reference Guide 2020.
Thank you.
Sure. Are there other questions about this?
Yes. May I ask my question?
Yes, of course.
Yes. I was like wondering why the protocol is not part of the 3 elements that is very, what can I say, but what is needed for good georeferences. Why the protocol is not part of these 3 elements? Oh no, okay, no, I see. My mistake, sorry.
No, but it's a really good question. It's a really good question. So ideally, we would need to provide all of those elements. That would be best practice. To provide a good georeference, we would need to report the protocol, the sources, the date, so that anyone that uses that record actually knows how we came to that. The minimum are those 3, but of course, we encourage everyone to go for the good practice, the best practice, and report all of the attributes that are in the green box here.
I got it. Thank you.
Okay, sure. And any other questions with this or about this, rather? Anything going on in the chat? Okay. Okay, we can come back to this as many times as you need. So I will go on to the next question now, but we can come back if you need it. So the next question is in the same Menti. We have a series of steps here that on the screen are not ordered in the correct order, and we will ask you to order those steps in our georeferencing method. This means, what do we do first? What do we do next? And so on. These 7 steps that we need to order.
This one will take some time and thinking.
That's okay. But it's important because we're going to use this every time with georeference. So we have to have clear what to do first, because otherwise, and we have seen this in the previous session, that different groups and different people started approached the location descriptions differently. So some started looking for the information on a map, some started looking at what was written, it was very different approaches. And so having these steps more or less ordered, in our heads, help us to do it more consistently and to not have to spend so much time going around, sometimes in circles. And so it's important that we keep this protocol, this set of steps in mind. We have one answer.
Four answers.
And it seems that we have agreement in the first steps at least, because they haven't changed, and the other words are reverting order somewhat. So far, it has changed a bit. The only thing that I haven't seen changing is the 7th place, the last step here. And how many answers did we have before? Hmm?
And now we have a potential for 18.
Okay. We can still have a couple more, at least. Okay, I'm gonna start looking at our results. So if I'm not mistaken, we're mostly correct, although we have a little problem in the last couple of steps. So first you voted for, some of you, some not, separate location information into parts. This is correct. This is the first thing that we need to do, is look at the information that we have and separate into parts. This, do I have coordinates? Well, this is the coordinates part. Do I have information about higher geography, administrative divisions? Well, this is administrative division. This is the most specific part of the location. So we separate all the information that we have. We can have elevation and depth as well. So that is the first step. The second step is to classify those parts, just as I just said, this is administrative division, this is elevation, and go into the most specific part that we have, and with that part, classify it. Classify it means determine which type of locality we're dealing with. Is it a geographic feature only? Is it a distance at the heading? Is it distance only? Is it coordinates only? So the most specific part that we have, we determine which type of locality it is. And here, remember that whenever we have coordinates in a locality description, that is the most specific that we can get, the coordinates. In general terms, Of course, we have to be careful, because if those coordinates have very low precision, the description may be more informative, the verbal description. But if we have good coordinates with a reasonable precision, that is always the most specific part of the locality. And so we should go for coordinates only type. Okay, if there are features that we're going to use, if we don't have coordinates only, if we have any of the other types, we will have to look for those features and define the extent of those features. So the third step is correct. We have to define the extent of the features. Once we define the extent, we are able to see the boundaries of those features. We find the centers and the radials of those features. Why? Because we will need those data, that information, for the overall calculations. And then we have the fifth and sixth steps. Here are switched. Why? Because here you have put as fifth step, calculate the final center and uncertainty. That is the overall uncertainty. And the next one says, identify the sources of uncertainty. So in order to be able to calculate the final center and the overall uncertainty, we need to know which are the sources of uncertainty. Because if we don't know that, we cannot put them into the calculation. So these two, fifth and sixth, are switched. So first we need to know the sources of uncertainty, and then do the actual final calculation. And at the very bottom, the last step, this one is correct. I think none of you has had any doubts about that. The last thing we have to do is document the georeferencing process, which means provide the sources, the protocol, the days, who georeference, etc., and any remarks that are not relevant to the location we're georeferencing. So you've done a good job in this one. I know that some of you have some of them switched. So I don't know who, so please review that. We have here the steps that we were just looking at, that we have seen in other presentations before. So you have it also in previous modules to review. Does anyone have any question about these different steps, or why they are ordered this way? Or
Yes, I do have one question on the identifying the source of uncertainties. Could you use the example we did on Monday, if possible, to show us again how to identify there's a source of uncertainty, because it's not clear yet in my mind. Thank you.
Sure. That's an excellent question. The sources of uncertainty will depend on the type of locality that we're dealing with. So that is why it's important to classify the most specific part. I will go to the example that we had the other day. Let me see, that was questions and answers 2. I have the example around here. Where? Oh, I don't have it here. Why? Oh, no, because it wasn't that. It was session 5. That's when we did it. So, okay, course module 5. I was looking at a different presentation, sorry. This one can be closed. Okay, so going back to the location that we had the other day, the example that we used was this one. So the locality description said Dando, Citato, northeast of Blonda, nearest river Luachimo. So again, what we first have to do is separate this into parts and then determine which is the most specific one, which in this case was Dando, and the type of locality is geographic feature only. So because this is a town. So once we have determined that, we can know which are the sources of uncertainty. And we can see that very easily in the calculator. But yes, let me go to the calculator because I think it will be easier. If we choose geographic feature only, which are the parameters that we need to provide? Well, one of the parameters is the coordinate source. This means where are we getting the coordinates for that feature, for that town, for Dando in this case. So that is one source of uncertainty, because what we can see in Google Maps has or Google Earth, in this case where we looked at it, has some resolution. They have satellite images that can be newer or older, and they have a particular resolution. So we have an error there that contributes to the uncertainty. So that is one of the sources of uncertainty, is the maps, the gazetteers, the sources where we're looking for the coordinates. If we chose here other maps, these maps will have also uncertainties associated that have to do, for example, with the scale that the map has. So if we choose a map that has a very large scale, means that we're representing a very big space in a small piece of paper, we're not going to be able to see much detail there. That means that we can probably make more errors. And so we have more uncertainty of the place we're determining. So one of the sources of uncertainty is the source where we get the coordinates. Then we have the coordinate format that we need to specify. So we will have uncertainties associated with the coordinates. We will have, again, with the coordinates, we will have uncertainty associated with the precision of those coordinates. The more precise the coordinates are, the smaller the uncertainty. But if they have very bad precision, very low precision, the uncertainty is going to be much bigger. Then we have another source of uncertainty, that is the datum, having or not having a datum. Careful here, it doesn't mean that different datums have different uncertainties. No, the difference is between having or not having a datum. And then we will have uncertainties that are related to the size of our feature and how well we can measure on a particular map. So this measurement error, which is the error that we make when we determine the extent of the feature, that is going to contribute also to the uncertainty. And you will have seen when you completed the spreadsheet about different parameters that depending on which unit you have, you can also have different uncertainties, because it's not the same to measure 0.1 kilometers or to measure 100 meters, because the precision in that measurement is different. And so all of those are sources of uncertainty for this type of locality. Now, if we were dealing with another type of locality, for example, distance at a heading, we would have other sources of uncertainty as well. For example, the direction. It is not the same to say north, right up, north, or to say northeast, or to say northeast. Why is this not the same? Because we're being more specific here in northeast that we're being when we're saying north. Of course, we can always be really, for real, straight north, but the probable error associated is much bigger if we're less specific in determining the directions. So those are sources of errors or sources of uncertainty that will appear in this kind of locality. Here you see that if we have an offset in this type, again, it's not the same with which precision that offset is determined and in which units. So all those are sources of uncertainty. So each locality type will have different sources of uncertainty. If we were georeferencing coordinates only, we will only have the uncertainty sources associated with the coordinates and our own error on how well we can put the point on the map. Does this answer your question?
Yeah, very well. Thank you.
Sure. Anyone else has questions about this?
I have a question.
Okay.
On the georeferencing calculator, when you for the locality type distance at a heading, I believe. Yes. That precision to the right under distance units. How do you determine that one again, please?
This precision refers to the precision of the distance that is reported. And so, for example, let me annotate here one. If the location description, for instance, said 10 kilometers south of a town, no? That's one option. Then we have 10.2 kilometers south of the town. And then we can have another option that is, let's put it in meters. Yeah, that would be 10,000 meters. 10,000 meters south of, this is a very exaggerated example, no? So if we have that in here in the offset distance, for the first one, we would put 10 kilometers. And what is the precision of that measurement? We have to try to think what the person that wrote down this distance, what was in their head. So were they measuring every 1 kilometer? Were they measuring every 5 kilometers? Every 10 kilometers? And so it was 10 or 20 or 0? It was 10 or 11 or 9? We have to try to understand which the error can be around this measurement here, this distance, this offset distance. And so this precision will represent the precision of this distance. And so in here, this could be 10 or 11 or 9. And so we have a precision associated with that measurement and that distance of 1 kilometer. Can be 1 kilometer less or 1 kilometer more. If we believe that people are measuring every 0.5 kilometers, that means it's either, if we're going every 0.5, we would have 10 or 11. If we go beyond 0.5, then we will have to choose half a kilometer here. I will keep it at 1 kilometer for ease of understanding now, and then we will see the tables in the best practices. So this will be for the first one. For the second one, we're measuring, sorry, 1 decimal place more. So whoever wrote this 10.2 kilometers could have been 10.1 or 10.3. So our precision in this distance is 0.1 kilometers. 0.1 kilometers is 1/10 of a kilometer. So this will be our precision for the second case. And here the offset distance will be 10.2. If we were measuring in meters, see that this distance is the same as the first one, is 10 kilometers. But here, the difference is that we're measuring in meters. So let's put it, I'm going to modify this to make it more obvious. Let's see, how do I do this here? I'm going to put 10.2 kilometers to make it similar to the previous one, to the second one. So in this case, we can think that this was 10,200 meters or 10,201 or 10,199. We can also think they are measuring every 100 meters. So it was 10,100 meters or 10,300 meters, the error to both sides. So in here, moving to distance units meters, we would have to choose how many meters we are, how many meters is the precision around that measurement. Given that this is such a large number, I would say they can miss by 100 meters. So the precision associated with this measurement would be 100 meters. Now, if that measurement was instead like 202, we know here that if they are specifying to the meter, the precision is in this last digit. They are being so specific. And so in here, the precision that we would choose would be 1 meter, because this could have been 10,202 or 10,203 or 10,201. So we can miss it. The error that we have around this measurement will be 1 meter. So the precision is, this precision here for this type of calculations is always referring to the offset distance that we're reporting. We have to be very careful because we will have to specify the distance units as well. And if you do the calculations, you will see that it's very, very, very different, the uncertainty that we get for different precisions here. So this is pretty big to compare, but if the precision is 1 meter here, or is 100 meters here, you see that here, 153, 826. If I go to 100 meters, 150, 845. You see that it has increased a larger uncertainty if the precision is lower. I mean, lower means that it's less precise. No, it's from 1 meter to 100 meters, it's less precise. If we go back to the 10 kilometers, we put it in kilometers, we say they are missing by 1 kilometer, you see that it's even bigger. And if we go to a 1/10 of a kilometer, which is 100 meters, still is bigger than measuring it in meters. Even if we have 100 meters or 1/10 of a kilometer, if we're measuring in these units, in larger units, we will have a larger uncertainty. Does this answer your question?
Yes, it was very clear. Thank you.
You're welcome. Are there?
A question from the chat that I answered in chat, but it's good to cover anyway. Shall I do it? Okay. No. So Beston asked, do I have to record the sources of errors in the georeference remarks? Is it that every time we georeference, we need to put the sources of errors? And the answer is, actually, if you include the georeferencing protocol, that will tell anyone who analyzes your georeference which sources of uncertainty were accounted for. The protocol says exactly how to interpret the locality types. So you don't have to record that information. It's taken care of by the protocol. And there was another question from Pascal asking if we could talk again about the source measurement error. Shall I do that as well? Okay, so I need to interpret what you're saying because there are two possibilities for that question. We have the coordinate source, you can see in the calculator, Google Earth and maps greater than 2008 is what's selected right now. That has uncertainties associated with it. So for example, for the Google Earth and maps greater than 2008, it has been demonstrated that the actual maps that you see can be off by up to 8 meters and for the newest maps. Before that, before 2008, the number was higher. I don't remember what the number is. We could find out with a calculator, but it's a bigger number. So there's that source of uncertainty from the coordinate source. But there's also the measurement error on the calculator on the other side, the other column. That measurement error is different. That's what happens when we make a measurement on the source. So, for example, if I'm using a paper map and I have a ruler and I'm measuring on the map with my ruler, that measurement error is my ability to distinguish between one number and another on the map. Conversely, if I'm using an online tool, which is going to be more common for us, like Google Earth or Google Maps, it's my capacity to measure the exact same spot, measuring multiple times. It's like my average accuracy when I use a measuring tool or draw on GeoPic or anything like that, how far off my dots are if I repeat the process over and over. That could be tested. You could test yourself to find out when you measure, make a distribution map of all the points that you measure and say, okay, what's my mean, what's my standard deviation from the center of all those points? And that would be my measurement error. But to summarize it, basically, measurement error is my capacity to measure on the map. How close can I get when I measure each time? I use 10 meters most of the time. If I'm being very careful, or if the location is very specific and I want to make sure that I'm not adding any errors just because I'm being lazy with my measurements, I'll be very, very careful and I'll reduce my measurement error because I'm being careful to something like 5 meters. I hope that answers that question.
Yeah, sure.
Okay. Looks like we have yet another question, this time from Raymond.
One moment.
You have
Moment. I want to share something with you, talking about measurement error. So these that you're seeing on the screen are, let me see if I can get rid of that. I will delete that. Okay. These that you're seeing on the screen are the KML files that you share with us for the previous exercises. What I want to show you here is that if we were a whole group that is going to georeference, and when we complete our georeference, we put georeference by the African georeferencing workshop team. So we're all georeferencing together, see what our measurement error would be. So here we can see clearly that everyone has provided a different polygon for this lake. Some of them are pretty different, and we can go into the details of that later, but it doesn't matter right now. But you can see that we can have errors associated with the measurement all the time. And so, for example, if I zoom in or out, I will say that these polygons are more, you see there, it seems that all of the polygons get the lake very well. Now, if we go into the details of it, we can see that there are some areas where every polygon is absolutely different from the rest. So suppose that all of you were, or rather each of you were measuring this lake several times or making these polygons several times, and you were drawing all those polygons, then you would come here and say, well, my measurement error is the difference between, or rather half the difference between my own extremes. So the first time I drew it, I drew this blue line. Then I drew these others, and at some point I drew this red line that is thick here. So I'm going to measure what my error is. And so I'm going to measure, for example, if this was the largest error in all the polygon, I would say I have 2,000 meters. That is 2 kilometers of error here, of measurement error. Of course, that since we are individuals, we tend to do things more similarly than when we compare with other people, but this is an example. So we would do it many times and estimate what our average error is. It is important that we calibrate that now and then, because sometimes we are more tired, sometimes we have less experience determining things or measuring things. And so every now and then we should this. Also, in different parts of the world, we have different kinds of images available. In general, for Google Earth, we will have good images for all the globe. But still, if you were working with other kinds of maps, or sometimes in Google Earth as well, the resolution that you can see is different, or sometimes there are clouds on the images and stuff. So in some locations, you may have more error than in others. So you should try to calibrate that as well, if you see that there are some factors that are impeding you from really seeing where the limits or the points should be. So I just wanted to show you this, and we can come back to discuss more about the polygons. Okay. John, you want to add anything to this?
No, not unless there are other questions about that specifically. That's a good example.
So there was another question on the chat?
Two more now, both from Raymond. I will go with the second question first because it relates to my previous answer. And that was, what is the link between measurement error and precision? It isn't clear for me. There is no link. That's probably why it's not clear. The distance precision, the last box on the right-hand column of the calculator, is about the precision in the locality description. So when Paula had the examples written at the right, like 10 kilometers and 10.2 kilometers and so on, as being written in the locality description, that's what this precision in the bottom of the second column is about. That has nothing to do with me measuring on a map, with me drawing lines or using a measurement tool in Google Maps. That's what the measurement error is about. It's personal. It's about me, the georeferencer, and how good am I at reproducing the same distance on the map each time. Is that clear? Nice stick figure. I'll assume that is clear and go to the first question, which was, what is the link between offset distance and precision. And I think that should have been answered when what I just said. The offset distance is exactly what the precision box is about. It's the how many digits of precision are represented in that first offset distance box, which comes from the locality description. So those are very different things. And usually the measurement error is going to be something very small, something in the realm of 10 meters or somewhere around there, where the offset precision could be any of those values on the precision selection box, which will depend on the distance units that are used. So can you do that very quick? Right now, we have kilometers chosen as our distance units, and you can see everything in the precision box is also in kilometers. But if we change the distance units to meters, then all of our choices are based on meters. And that's why that distance units box is so important. It has to be the units that were used in the locality description. We have no other choice about that, because otherwise we can't represent the precision correctly.
One small comment is be very careful to convert your measurement error to the units that you're selecting here. Like, for example, a moment ago we were in kilometers, and so in kilometers our error was 2 meters. If I move to meters here, my error is not, this is 2 millimeters here, so I would have to change it to 2 meters. So the units have to be consistent. So distance units applies to all of these things here. They all have to be in the same unit. And so make sure that you determine this based on what the description says, and then you adjust this value to match the units that you're using. Otherwise, you will make a huge mistake here. If you put this in meters and you put that measurement error, that means that you're measuring with a caliper, basically. So careful with that. Remember to change the measurement error to the units that you're using for the from the description. Are there any more questions about this, or about what we were seeing about the steps? The last things that we were checking were the different steps. Are there questions about this?
By the way, those are all great questions so far. There are no bad questions, but these were great questions.
I see no hands up, and I believe there's nothing on the chat. So what I will do now, yes. Okay. Okay. So what we propose now is that we check that spreadsheet that you were supposed to use to see how the uncertainty changes. That was one of the exercises from previous modules, so that we can discuss some of that, some of those factors that contribute to the uncertainty. We can either do that now or take a break and do it after the break. What do you prefer? Do you guys need a break now?
Maybe take a break now, and then when we come back, we can carry on with that exercise.
Okay, we have one vote for a break. The rest, how do you feel? Break? Okay. Okay, so we'll do that. We'll take a 10-minute break, and we'll come back and review that spreadsheet to discuss a bit more and so that we can still we keep going with the calculator and how to use it. We can go through that. Okay, so see you in 10 minutes then. Okay, we are back. And most of us are back anyway. So we're going to go now to the sheets that you had to complete. John?
Before we forget, it's worth making the announcements about GeoPic. I reported to the GeoPic developers that it wasn't working in Safari and Mozilla, and I was able to find out what the problem was, and they were able to fix it. So you should be able to use GeoPic in Safari now, and please do confirm that. I confirmed it for me that it worked here. Please confirm it for yourselves as well. And also, so I don't forget it, someone earlier on in a questions and answers period asked me about the tool for calculating probability surfaces, that type of georeferencing method. And the answer is that the software was called Modelco. I'll type it. Modelco. And that the software does not seem to exist any longer, but that there is a paper about it. And give me 1 second. The paper is the following. So if you're interested in that more in depth, those are the resources available. Okay, that was what I wanted to say. Thank you.
Thank you. Okay, we're going to go to the spreadsheets now. Let me share my screen. Let me know if you can see it. Okay. So the idea of this exercise was that you could perform the calculations with a set of given parameters that were listed here, and that you would see how the overall uncertainty varies depending on different factors. So in the first one, the idea was to see the change in uncertainty when we vary the radial of a feature and the datum, whether it is known or we have a datum, in this case, WGS84. So in here, I have put the values for each calculation. I'm going to show only one calculation, and the others are the same, but changing the values for what is in this rows and columns. So for the first one, we have to choose these fixed parameters. So we're going to go to the calculator and say that the locality type is geographic feature only. So we pick geographic feature only. Then the source was Google Maps. Then we have here that the coordinates are in decimal degrees. So here we choose decimal degrees. We had some coordinates provided that we have to just copy paste. Latitude. Then we have the longitude. Okay. For the datum, we have to see which one we have to put. In this case, for the first value, I'm going to put datum unknown. So the datum is not recorded here. Then we had a precision of 0.00001. That's 5 decimal places. here, there we go. And then we had, well, a measurement error of 0.002 in kilometers. I'm going to put that 0.002. This is in kilometers. And the radial was one of the parameters that we had to explore. So I'm going to use this radial to get this value. So it's 0.025. So those were all the things that we needed for the first calculation. We calculate and we get this uncertainty. This is the uncertainty that I recorded here. To see how this varies for the same radial, but having the datum available, all that we need to do is change this datum here to WHS84 and recalculate, and we get a much, much lower uncertainty. So this is a much better georeference, no? So in here, we record 36. We do the same for different radials. This means the radials are, if we were to draw it, this would mean that we would have, put it in, one feature that is this big, one feature that is this big, or one feature that is even larger, right? These are the different radials. This will be the first radial, this will be the second radial, this would be the third radial. If these were circles, just forgive my drawing abilities here, or inabilities. So these would be the radials that we're looking at. Okay. So when we complete these values here, the values for each calculation, here you get a plot that is showing the net uncertainty as a function of the radial for each of the conditions of datum, either unknown in red or WHS84 in blue. So what can we see here? The first thing that we see that is pretty obvious is that the larger the radial, so the larger the feature, the bigger it is, the larger the uncertainty that we have. And so, again, if the feature is bigger, the uncertainty is going to be bigger than if the radial is smaller, if the feature is smaller. The second pattern that we see here is that when we do not know the datum, when the datum is not recorded, systematically, the uncertainty is larger. So for any radial, always not having the datum makes the uncertainty be bigger. So is this clear? And the difference is the same for any radial, because the difference in the datum, what it's going to do is not providing us with the necessary information to know where the coordinates are. So that center is. So it's just an uncertainty on where those coordinates fall on Earth. So that difference due to the datum is the same no matter the radial. It's always larger if we don't know the datum, but it's the same independently of the size of the feature. Because if you remember what the datum is giving us is expressing where do we measure those coordinates from and with which scale? What is our reference in the coordinate reference system? Where is our zero? And how are the axes oriented? And what is the scale? Is this clear for everyone? Okay, I don't see any hands up nor any comments on the chat. So I'm going to move to the next tab to show how the uncertainty.
A question just came up.
Oh, okay.
The question comes from Fabrice and is, why do we have measurement of uncertainty in meters while having other parameters in kilometers?
That is a very good question. And the answer is the calculator always gives the uncertainty in meters. Why? Because we're following best practices and we're trying to report the results using Darwin Core. And in Darwin Core, the field is coordinate uncertainty in meters. So we could turn this into kilometers, no problem. This would be 0.036 kilometers. But when we had to share that information, those data, and we put it in fields in Darwin Core, the field to put the uncertainty is in meters. So the calculator already gives it, makes the calculation and gives the result in meters.
One might ask why. Why is it in meters in Darwin Core? And the answer is that when we share the data, what we would like for a parameter about uncertainty is to be able to compare all uncertainties in all data in the world. So this would allow me, for example, if I was doing a search on GBIF or something like that, to say, please give me all of the records that have a georeference with the uncertainty less than or equal to 1 kilometer, because I want precision in the final results of a kilometer or less, because maybe I'm doing niche modeling, etc. So that's why it allows us to make that question on all of the aggregated data in the world. If it's in different units, we can't ask that question.
Is this clear now? How we answer? Okay, excellent. Okay, so I'm going to pass to the next tab, where we do something similar with respect to calculating the uncertainty with different parameters. But in this case, we're varying the radial, the size of the feature, and the precision of the coordinates that we get. And here, this is the most precise coordinate, this is less precise, and the nearest degree means that I'm going to write it down here, because we've seen, I've been looking already at some of your spreadsheets, and I believe most of you have made the same mistake here, which is the following. When we write the coordinates, I'm going to write them down here. So suppose I'm using the coordinates there, 0.05708 and minus 71, just for the sake of following with the same number. So these are the coordinates that were given. Which is the precision of these coordinates? Well, the precision of these coordinates is 0.00001. We have 5 decimal, sorry, we have 5 decimal places. So this is the precision of these coordinates. If we change the precision as is given up here, we need to change the coordinates that we give. Because if we change the precision and say, for instance, let me select this one, and say the precision is 0.1, and we keep these coordinates here, they don't match. I mean, these coordinates don't have this precision. So to be able to do the calculation with this precision, we need to adjust these coordinates to that precision. And so if it's 0.1, this is 0.5, so I'm going to round it up. Not truncate it, but round it up. So these would be the coordinates, the corresponding coordinates with this precision. This is something that most of you have not changed. So you used exactly the same coordinates and changed the precision, but this was important. That's why we put here, starting at here, starting at these coordinates. When we change the precision, we have to adjust. If we put to the nearest degree, so here the nearest degree. Oh, let's put here nearest degree. Nearest degree means 1 degree precision. That's what nearest degree means. And so in here, we would have to adjust this. This would end up being 41, and this would be end up being, because was 0.5, would be end up being that coordinate. So we have to introduce those coordinates, those changes in the coordinates when we change the precision. So doing that, entering all these fixed parameters here, all these fixed parameters, entering the coordinates and adjusting depending on which precision we use, entering the different radials, we do the calculations, and we get these values on the screen. So what do we see here? Again, the uncertainty, the overall uncertainty as a function of the radial for each of the precisions. So we have here in blue the most precise coordinates. And as expected, the larger the feature, the larger the uncertainty. And this we have seen before. Again, that happens for the other precision and for the other precision, which in here is not that obvious, but it's a matter of scale, because these uncertainties are so big that maybe here is not that clear a difference. But if you see the values, this one is larger than the previous one, and this one is the largest one. So it increases as we increase the radial. That's for any precision. And then what we can see is that when we change precision here, so here for a given radial, if we change the precision, we go to less precise, the uncertainty changes a lot. So when we move from this, from 5 decimal places to 1 decimal place, we have a change. And we have a change that here seems small, but if we look at the values, it goes from 36 meters to almost 14 kilometers. So this is a big jump here, even though it looks small. It's a big jump. And when we move to a much lower precision, to a degree, we go to 140 kilometers. What we have to keep in mind here is that we're talking about, let's see if I can draw that on the, so we have our globe here, or our Earth. And so we're moving from, this is getting difficult. So if we have a precision of, with five decimal places, we're saying, well, the coordinates can be off this little bit. Now, if we say we are with 0.1, we say we can be off this little bit. And if we are to 1 degree, we can be off this little bit, which is a lot. And this will have different changes if we're looking at latitude or longitude, because of how the Earth is, that is flattened on the poles, at the poles. So are there questions about these kinds of variation with respect to precision? I cannot see the chat right now. Has everyone understood why we have to change here the coordinates accordingly to with respect to the precision? Okay, one feedback says it's clear. Okay, so let me first clear all drawings. There we go. Then I will move to the next one. Here we have to see variations, again, radial, the size of the feature, and distance in kilometers. So this is a different type of calculation, is distance only. So a locality of this type would say, for example, X kilometers from a place. So basically, we're looking at something that we have a feature with a particular radial, which can be bigger or smaller, and we are X kilometers off that place. Can be 1 kilometer, 10 kilometers, or 100 kilometers. So that's what we're looking at here. So we put all the parameters in the calculator, we get all the values for this little table here, and what we're going to see is, once again, as the radial is bigger, the uncertainty is bigger. And that, I think, it should be clear by now. Now, when we increment the distance, the further we get, now we're looking in the vertical, right? When we have 1 kilometer, 10 kilometers, or 100 kilometers, the uncertainty increases quite a bit. And you can see that it goes from 1,000 to 10,000 to 100,000 meters. So that is 1 kilometer, 10 kilometers, 100 kilometers. And that happens for any radial that we're looking at. And at the same rate besides. See, here we go from 1 to 10 to 100. Here we go from 2 to 11 to 101, and so on. So the further off we go, the more uncertain we are. Is this clear for everyone? Okay, you want to take it?
Yeah, Fabrice asks the question, does it mean that when we use 0.00001 precision on decimal degrees, that it's the best option for precision among the rest? And the answer is tricky to that question as it's posed. You're forced into the precision that you choose. So it's not a matter of being a better choice or not. You must indicate the precision that is present. Now, conversely, which of the options is most precise? Yes, the more zeros there are in decimal degrees, the more precise the coordinates are. But you can't just choose as many decimals as you like if that many decimals aren't present in the coordinates. So that's why Paula made this clarification that when doing this exercise in the spreadsheet, the coordinates had to be changed, their precision had to be changed to match the precision that was in the spreadsheet. You had to remove all of those decimal places in order for the precision to match the coordinates. So does that answer the question, or have I gotten the question wrong?
I have one more comment about this, just for clarification. If we get the coordinates, for example, from Google Maps or Google Earth, we never want to truncate them or round them up. We provide as many decimal places as we can. That means the decimal places that the source provides. So yes, in that sense, it's always better to have more precision, always. So if we have those coordinates with more precision, we use them the most precise, we use the most precise that we have.
At least up to those 7 decimal places. After the 7 decimal places, it doesn't actually matter, because then we're talking about sub-centimeter distances on the Earth, and it won't matter. So Pulcheri has her hand up.
Okay, thank you. I was wondering, now I understand that all the uncertainty of one table concern one feature, is not like 3 feature for like 3 radials. Do you understand my question? Because I thought that, for example, in this case, the radial, the sensitivity with radial 1.5 concern one feature, and the intensity with radial equal to 10 kilometers concern another feature. So I didn't understand that the radial that we got in one table concern only one feature. That means that if we move forward of our center, the feature will also increase, and the sensitivity also will increase. So I really understand now what was expected in the table.
Yes, the idea was to have an example that is a bit exaggerated. So, and I will go back to the example that I was showing you before with this determining the boundary, the extent of this lake. So for this one here, there is this red line here. If we said this was the lake, the radial will be much bigger. So the idea was to show, well, it can be different features or the same feature. If we determine it differently, the idea was to show that the uncertainty is going to change quite a bit. So one of the take-home messages here is that we have to be very careful in determining the boundaries, the extent of the different features. Because in the example, it was pretty exaggerated from, well, from 20 meters to 10 kilometers. That's a very big difference. I doubt that any of us will make that mistake, but it was exaggerated for that purpose, to show that we can miss it. We can be affecting the uncertainty quite a bit when the radial changes. Just so you can think about it in both ways, with different features or with the same feature if we determine the extent differently. Also, this is useful for what we have seen. Let me go back to module 5. This is not the integration, not this one. When we saw an example for historical localities that would give us errors of this kind. Let me see what it is here. Where we had this example for Kumasi in Ghana. If we were to determine the extent of Kumasi in one particular year, in the 80s, we would say the extent is X kilometers. But if we were to determine it today, the extent will be pretty different. The radial will be different. And so we have to be aware that the overall uncertainty will change when we draw or when we delimit a feature that has a larger extent and therefore a larger radial. So especially for historical records, or especially for big cities or towns that change quite a bit in size because they grow, that is going to affect our uncertainty. So the idea was that you could see how much it changes depending on how much the size changes as well. Are there any more questions about this one of precision or this one with the offset that we just saw? Otherwise, I'm going to move to the next one, that is distance and degree. And for distance and degree, what we are varying is the radial, the distance, and the distance in a particular direction. And so in here, you should have seen that when you calculate the values, the uncertainties are the same in each row. So that's why you see only one dot, is because the other ones are underneath it. And the idea here was to show you that here we're providing orthogonal directions, which is the best thing that we can do for a location description. So again, we will have an increase in the uncertainty as we increase the radial. But even if we move different distances, when we have orthogonal directions, the uncertainty won't vary with respect to those distances because we are providing orthogonal directions. If we were not providing orthogonal directions, we will see the differences that we saw before. And now we're going to see the next example, which is we have distance in kilometers. We keep the radial. Now we're saying, well, the town is the same. We have the same radial, it's the same size. But now we're going to move different distances with different precisions in the direction. And I want to make a little drawing here. Let me see how I will draw this. That is the following. Suppose that we are moving south. When we move south, I'm moving south there, from here to here, and we say X kilometers south, we have to account for some error in that south. So what we do is say, well, the person that said south it did not say west or east and did not say west. So it's not west and it's not east. So there is a triangle here where that uncertainty can lie. So it could have been up to here or up to here, basically. So my error will be all this arc here. If I say south, I could have been southeast or I could have been southwest. Not more, because then I would have said east or then I would have said west. But so all this arc here is part of the uncertainty of just saying south. Now, suppose that I said, I will undo these arcs here, and suppose that instead of saying south, I said southeast. So if I say southeast, oops, not that one. Let me do a straight line here. If I say southeast, this one is southeast. So I didn't say east, I didn't say south, I said southeast. And so my mistake could have been half to this side or half to this side. And so my arc of uncertainty would have been that. Check that the other one, the previous one, I'll draw it again. I should have kept it there. The other one, the error associated with south was this from here. Oh, sorry. Let me draw with this one. From here to here, that's south. Saying southeast is much smaller. And if I say southeast, I'm stepping on this line here. And so my error would have been half of that and half of that, right? I'm sorry for the drawings. And so my error will be that, my arc of uncertainty. So you see, if I just say south, I have this big uncertainty associated. If I say southeast, I have this uncertainty. And the more specific I am in the direction, the smaller the associated uncertainty I have. And so here in the graph, we can see that moving from south, southeast, south, southeast, and we see that the uncertainty decreases because we're being more specific in the direction. And that varies also depending on the distance. And you can see the values here. but it's basically an order of tens that has to do with the differences in distances that we saw before. The larger the distance is, the larger the uncertainty, and that decreases much faster for the larger distances. Why? And I'm going to do now another graph. I will clear everything here and show you one thing that we've seen before, that is the following. Suppose that, well, these lines are not very straight. Sorry for that. Suppose that we're moving in a given direction here, like that. And so if we take into account the uncertainty that we have, for example, suppose that we're moving here northeast. So we can be missing that by that, right? So we part it in half, and our uncertainty is going to contemplate this arc here, right? So now see what happens if we move further. So here I moved 1 kilometer northeast, and this is my uncertainty here. Now, if I move 10 kilometers northeast, I will be moving up here. And so see what happens with the associated uncertainty. It's much bigger. Even though I have the same direction, the same precision in the direction, as I move further, I get a larger uncertainty. And if I move 10 kilometers, 100 kilometers, sorry, I'm moving up to here, 100 kilometers. So the associated uncertainty is going to be much bigger. And so as we reduce the distance, we get less uncertainty associated with direction precision. Is this clear? Are there questions about this? Someone raised a hand. I cannot see who.
Sherry, you had a question?
Yes, I do have one question. Can we now go to the calculator, the georeferencing calculator, to enter everything that we just said here and see what the results are or the output, please?
Yes, I will do that. I will. Here we are at a distance at a heading is the type of calculation. And then we have all these parameters that I think are already there. We have, let me check. These are all fine. And then we have to change these parameters down here. We have first, the offset distance is 1 kilometer and nearest degree south. So direction south, distance 1 kilometer. The radial was fixed. I believe it was here. 1.5, it was the radial. 1.5. The measurement error is fine. We are in kilometers, and the precision, I think everything is fine now. The distance precision, we set it to half a kilometer. Okay. So here we're changing direction. The precision of the direction really is like if it's south, southeast, south-southeast, and the offset distance, either 1, 10, or 100 kilometers. All the rest is fixed. So we calculate, and we get this uncertainty. Now, if the offset distance is greater, we're moving in a single direction, but we're moving further. Is this graph that we have here on the right that I just drew? We're moving in the same direction. Here is another direction, but for the sake of showing the same, we're moving further. So we expect the uncertainty to be bigger if we move further. So we put 10, and indeed the uncertainty is much bigger. This is 8,000, and the other one was 2,000 meters. If we move even further, and we went from here to here, we're moving further, we get a much larger uncertainty. So that if we keep the direction and we move further, the uncertainty increases. Now let's do the other way around. We keep the offset and we specify the direction more. So let's calculate this again. This was 2,000. Now, instead of saying we're going south, we're more specific and we say we're going southeast, and we calculate. And so we're being more specific, and so the uncertainty is smaller because of the drawing that I did before. We're being more specific, so instead of having a whole fan that includes halfway to one direction and halfway to the other direction, we're being more specific. We have southeast, and so our fan of uncertainty, or our arc, is much smaller. If we are yet more specific and we say south southeast, we go here, south southeast, and calculate, we get a smaller uncertainty. Yet. And we can do that for all offset distances. So I'm here putting 10 for south southeast, and I get this uncertainty. If I am less specific and I say southeast, the uncertainty should be larger. And here we have it. If we are even less specific and we say south, the uncertainty will be even larger. There. Has this helped, Bushali?
In the reference of the georeferencing best practice, there is let me just, when calculating the uncertainty associated with directional precision, there were many examples that they say, first of all, the one with only one coordinate, for example, 10 millimeters north of something, it is equal to 45 degrees. And when it's two direction like north, if it's equal to 22.5 degrees, and yeah, and so on up until 11.25 degrees. So I was wondering, where should we use this uncertainty in our calculator?
That is just explaining what I explained before with south, but I'm going to put it again. So we have here, sorry, let's erase that and do it properly. So suppose that these are the directions, north, east, south, and west. So what the guide is explaining is, if I'm going south, I can be mistaken by these lines here. I mean, I could be going this far or this far. So the error that I can make is all this arc here. And this arc here to one side is half of, this is 90 degrees, and so this side is 45 degrees. And this other side is 45 degrees. So we have 45 degrees to each side that we can be missing. So if we just specify south, we can be mistaken 45 degrees to that side or 45 degrees to this side. So all this arc here will be our associated uncertainty because of direction. That's one. Now, this is to when we specify, let me put here, I will draw with this, that we go south. Now, suppose that we are more specific and we say we go southeast. When saying, oh, sorry, when saying, let me select that, and a line here. When we say we go southeast, we're saying we go here. I'll make it longer and just a little bit display so that you can see it. This is saying we're going southeast. So when we say we go southeast, what we are saying, what we are implying is that we can be mistaken half to this side or half to this side. Why? Because if we were all the way to here, we would have said south. And if we went up to here, we would have said east. So our mistake here can be half of this and half of that. So our error is going to be, or our uncertainty is this. And this, to each of the sides, is this little piece is 22.5, and this little piece here is 22.5 degrees. And if we are more specific still, and we say south-southeast, then we would be south-southeast, it would be here, and then yet again, it would be half of that, which is 11.25 degrees to each side.
I put the reference that Pulcheri was talking about in the best practices guide into the chat. There's a link there that'll show you exactly the section that she was talking about in the table where these numbers are given.
Now, is this clearer now where it's coming from, these numbers?
Yes, it is. Thank you.
Sure, excellent. You're welcome.
Just one thing to add. Remember, all of this is the theoretical background. You don't ever have to use those numbers in practice because the calculator does it for you. But you need to know why they're like that and what the effect is of being more specific about direction.
Thank you for the comment, John. I wanted to ask the same thing. Why is it important? But now since you've explained, it's okay.
Okay. I think that was the last tab for this exercise. Are there any other questions about this? How the uncertainty varies with different factors?
If there aren't any other questions, there's one other thing that I'd like to mention that's not coming up in this exercise, but that's interesting. And that is the uncertainty due to an unknown datum. That is based on the differences between all datums everywhere on the Earth. And it's almost impossible to predict. To know that number, you actually must use the calculator or write a program to figure out the biggest distances between all possible datums. The important thing is that the uncertainty due to an unknown datum is not a constant. It actually varies by position on the Earth. And so you can't assume a number. You could know what the maximum possible value in the worst case scenario is, but to actually know to minimize and optimize the uncertainty due to an unknown datum, you need to use the calculator. There's no other way, really.
Okay. More questions about this? Okay, yeah, I don't see any comment, but please feel free to leave them on the chat. Okay, there is one. Faris, you say you don't get this very well, but which part? All of it, or any particular one? Or what John just said?
Yes, I don't get
We can hardly hear you.
Oh, I'm sorry. I'm saying that I don't get very clear or very well about limiting uncertainty on datum.
Okay, let me go to the first presentation that we had on geographic concepts. See if that clarifies it. Okay. Let's start back here. So I will go back a little bit to the theory behind it. So the datum, what it's doing is setting the position, the scale, the position of the origin, the scale, and the orientation of the axis that we're going to use as a reference to put our coordinates. And so, for example, this datum A has this origin, has a particular scale, and orients its axis, X and Y, in a particular way. Other datums can do it differently, for example, because they use a different reference ellipse. And so if you look at this, since the reference is moved, even though the world, the real world, is the same, the position of different coordinates will be different between different datums. And so, for example, so you see here that they are displaced one from the other. There are different representations of the Earth. And so if we have a point on Earth, any point, a real point, and we want to represent that point in a given datum, we would have coordinates. Remember that the coordinates are angular distances. Latitude is the vertical angular distance with respect to the equator, and longitude is also an angular distance with respect to a prime meridian. For this dot, if we use the green datum, we will have this angular distance and this angular distance. Now, if we represent it with another datum, even though the spot is in the same place, the world is the same, for another datum, we will have angular distances that are different because they are using a different reference. And so they're putting the origin, the scale, or the orientation of the axis in differently. And so the distances that they give are different. And so when we get coordinates for those, for example, for latitude, we see that if we use one datum, we get one latitude. If we use the other datum, we get a different latitude for the same point. And the same will happen for longitude. And so the thing about knowing the datum or not knowing the datum, what is accounting for is all the potential differences that we can have among all different datums. So for example, if I give you coordinates for this point and I don't tell you which datum we're using, if there were only two datums available, we could have this difference, this much difference in longitude and this much difference in latitude. Now, the thing is that there are a lot of possible datums. And so what we do is well, what is the maximum error, which is the maximum difference that I can have if it was in one datum or in another for the coordinates. Does this help understand why what is the uncertainty associated with datum about?
Yes.
John?
I wanted to add something here, and that is a question that might be running around in your heads, and that is, why? Why so many datums? Why make it complicated? And the answer is two parts. One is historical. Over time, the models of the surface of the Earth have changed and sometimes improved. But even today, new datums are being made and they don't agree with each other exactly. Why? Why do that? And the answer is that datums generally are made to model the surface of the Earth in a very specific location. And one datum can do a better job of that than another. So throughout Oceania, for example, the islands in the Pacific Ocean, almost every one of those islands or island groups has its own datum because that datum describes those islands better than WGS84 does. And so for being very specific, for doing surveys locally, et cetera, you want the best possible representation of the surface of the Earth where you are. And WGS84 is kind of like an average, a reasonable, good average for the entire Earth. That's why there are so many different datums. And the problem is with 700 different ones and the coordinates not being in the same place on the Earth between all of them, we need to know what happens if we don't know what the actual datum for the coordinates was.
There, I was muted. More questions about this or any other thing that we've seen so far?
And now I just want to know how to limit how to limit the uncertainty in measuring datum. Yeah, it's all, in fact, just want to know this.
As I understand it, the question was, how can you minimize the error due to the datum? And the answer is, you cannot. You have to use what you know. And what you know has an associated uncertainty. What do I mean by that? Suppose we're given a locality description that has coordinates in it and does not say the datum. The sad fact is we have no way, except under very specific circumstances, to know what the datum was. We just, there's no way to know. And if that's the case, all we can do is in the calculator say that the datum is not recorded. And based on having selected datum not recorded, the value of the uncertainty is based exactly on the input latitude and longitude. It varies all around the Earth. And it might be less, it might be more, it's very unpredictable. Where the worst case scenario is and how big that could be. In some places, not knowing that datum only contributes 1.5 kilometers to the uncertainty. In other places, up to 5.6, more than 5.6 kilometers is what that part contributes. There's not much you can do about that. You can't minimize, you can't optimize. If you're writing a locality or if you're doing recording coordinates yourself in the field, the way you can minimize any uncertainties is to provide the datum. It doesn't matter if the datum is WGS84 or another datum for your country. As long as you tell us which one it is, that minimizes, in fact, completely eliminates the uncertainty from the datum. So provide the datum, eliminates uncertainty from the datum. Paula's scrolling through the list of datums. It's very, very large. Does that answer that question?
Yeah, yes, thank you.
Welcome.
more questions about this or other things? If there are no specific questions, we're at the time of the original time, but we said that we could stay half an hour more, but that depends on what you want to do, if you want to stay or not. Our position, if we're staying, is to do something similar to what we did last time, that you divide up in groups and you work on a particular location georeference. So here is a question from Faris in the chat. It says, so what is the most general one? I assume this he's referring to datum, that we can often use then. So if you're using Google Maps or Google Earth to get your coordinates, you will use WGS84 to get those coordinates. That's the one that is mostly used. And if you're using a GPS device, usually, not always, but usually they are pre-configured to have WGS84, but you have to check that. If you're using a GPS, you have to make sure which datum it is set to use. So WGS84 is the most common one.
On the other hand, if you happen to be in the field, unable to use a GPS and relying on a paper map, you would want to record the coordinates from the paper map using the datum of the paper map, because you won't be able to make a conversion yourself in the field. That conversion is a complicated thing, and you need a GIS or a website that does the calculation to make a change from one datum into WGS84.
So one such tool that allows us to convert coordinates between reference system is the epsg.io webpage. So it has a tool that we can use to transform coordinates. Sorry, this comes with ads now. And so we can change here what is the coordinate system or datum that we're using for coordinates, and what is the output that we want. So suppose that here we could found search for a datum that was much used here in Argentina. So this is one datum that we might have, and we may want it into WGS84 in Silva Mercator. So we can put the coordinates here and transform them. Oh, so I did something wrong with the coordinates. What did I do wrong? Oh, there. I think it's not taking my format somehow. Degrees, minutes, and seconds should be fine.
Get rid of the minuses.
There. Well, let's make this up. Okay. Yeah. Otherwise, I have to put I said a letter showing the hemispheres for this format. So here is converting this. I can choose another WGS84, search for that. And so I can use the, what is the code that I want? Can't see it with these ads now. What is it? 4326. See if it finds it like that. There. I wanted to the most common WGS84, which has this code, and so there it transformed it to the coordinates in WGS84 from another data, and I can swap it. This means the change and go back and forth. So you can change between any given data here and get the coordinates. You see that they change. Here we had 25 seconds, and here we have 31 point something seconds. And here we have even differences in the minutes. So you can see that the coordinates in those two datums for this latitude and longitude are pretty different. Okay. So what do you prefer? Do you prefer that we stop this session here and that we reconvene on Friday, or are you up to georeferencing one locality in groups as we did before? We have much less participants now, I believe. Anyway. So I could probably. Okay. Propose it.
Yeah, my feeling is that because those georeferencing in groups, first of all, require groups, and we are less people now than we were at the beginning, that we do that early on Friday. And if that continues to be a very useful exercise, we know that was extremely useful the first time we did it. We learned from the struggles that were seen in different groups what we needed to cover more. And so if we do that one more time, we can see how well the understanding has changed since the first exercise. And we can look at a different kind of locality doing so. And if that still is useful, we can do more of them. We had a total of 4 such exercises to work with, all of them a little bit different from each other. So it looks like we've got at least 2 people saying to do that on Friday. I think that's a good idea too.
Okay, then we will finish for today unless there are more questions. We can stop it here. Remember that the deadline for module 5 is tomorrow, actually. I would propose that if you don't make it for tomorrow, it's okay. You can hand it in on Friday or Saturday at most. We ask for that because then we have to correct them and send you the revised files and see if any of you need more help with something. So, but please come to Friday's session having looked at those exercises so that if you have questions, we can resolve them all together. So we finish here. Thank you very much. And we'll see you on Friday.
Oh, I have one more question. Sorry.
Oh, okay, sure.
On the exercises for module 5, I believe there's an extra exercise in the Excel. There's an Excel sheet for us to complete. What are the instructions for that exactly?
Give me a second, I'm opening the file. The instructions for that, I believe, are in the exercises document. Let me see. Checking exercises document. Exercise 4. Give me a second because it's taking a little while to download. Okay, so let me share my screen again and I'll show you. So in the exercise document for module 5, you have all exercise listed above, and exercise number 5 is the one that is linked to that spreadsheet. So here are the instructions. So each row in the spreadsheet is a locality record, which are these ones here. So each of these is a record, A, B, C, D, up to J. So each of these is a locality record that you need to georeference. So in here, it says indicate if the provided georeferences can be correct. And so to do that, you have to evaluate all that is provided. So you go, for example, to record A, and you check if this record is georeferenced. So you look at all the fields that you have here, and you have country code, island, locality, elevation. You have here coordinates, uncertainty in meters, etc. And you have to say, with all the information that you have here, if that record is georeferenced, if that georeference is correct, so you will have to do the georeference, not to the very detail, but check if the things are consistent. For example, if I'm looking at this record, right, at the first one, and I see this locality with this elevation, and I go see the coordinates, and I put the coordinates on a map, and they are in another place in America, well, there is something wrong. So this is not correctly georeferenced. It's not the case of this one. I'm just giving an example. So, or if you go here and you see, well, the locality, for example, says Ghana, a whole country, and you come here and you see an uncertainty of 1,000 meters. That is impossible if the locality was the whole country. So one would expect that the uncertainty is much larger. So you have to evaluate those factors and see if each of these records is correctly georeferenced or not. And if it's not, why? So you have to fill in here. For example, in that example, I would say impossible because the locality is Ghana and the uncertainty provided is 1,000 meters. So the uncertainty is too small to represent that location. That would be, for example, one way of justifying it.
All right, thank you.
Sure.
So a strategy for approaching that exercise would be see if you can find anything very fast that tells you, no, this is not a good georeference for one reason or another. Review what are the characteristics of a minimum georeference and see if all of those characteristics are there. And then if they are, you need to go a little bit more into detail. And like Paula said, maybe the uncertainty is ridiculous and you can see that right away. And then you can quickly go through and discard some of them as being not good or not viable georeferences. And then the ones that are good are going to be the ones that are harder and harder to determine. We have a hand up. Go ahead.
Well, okay, I think you just answered my question. I wanted to find out if you only have to testify when you think the answer is no. That is why you only have to give reasons why you think it's no. Is that right?
Yes, that's right.
Okay, my
There should
answer
be not all the reasons. The first reason you find should be sufficient.
what I mean is that if it's yes, then it's straight is yes. But if it's no, then you have to justify why it's no.
Yes, that's right.
Okay, thank you very much.
Okay,